All right. So coming back, I'm going to pick up where this approximately where Dr. Lee left off. He started covering the chain rule, and I'm going to continue with that today. Okay. Now, you saw the chain rule in Calculus 1 for functions of one variable, and Dr. Lee did various scenarios of chain rule and multivariable, but really they're all the same thing. It just depends on how you view multiplication, or which multiplication operation is the right one. So in single variable land, what we have is the derivative of f composed with g of x. So f is the outer function and g is the inner function, which would be the same thing as derivative of f of g of x. And that's just going to be, well, what is the one variable chain rule? What is the derivative of that from Calculus 1?
Derivative of the first keep the second plus
Not product rule.
Times
times.
the derivative of the inside.
Yeah, so f prime of what?
G of x.
Of g of x. And then,
Times.
not g, but g prime. Yeah, so you're multiplying the two derivatives. You have to make sure that you evaluate the derivative of your outer function at the inner function, not just x. Okay. Now, in the single variable case, multivariable case, so I'll state the most general case that covers everything, and then we will make things more specialized and see examples. So f is a function that takes in n variables, that has n inputs, and has m outputs. So keep in mind, domain is number of inputs, range is not consists of your outputs. Now, g, the output of g is the input to f. So those two are related. So the number of outputs of g has to be the same as the number of inputs to f. So this has to be Rn. And then the number of inputs to g, we'll call that something else. We'll call it P. Okay. All right. Now, so the way I can describe the multivariable chain rule is almost exactly the same as what we have for a single variable case. I just have to help you guys understand the notation that's used. So first, instead of f prime and g prime, and we don't have those anymore because, as I've said many times, prime doesn't really make sense in a multivariable situation. You have what is called a Jacobian matrix of f. And I'm going to use u to refer to my inputs to f. So the idea is y is equal to f of u is equal to g of x. Because x is what gets plugged into g ultimately. And then we will eventually put the two functions together. So the derivatives of f with respect to u we arrange into a matrix. So f has m outputs. So that means that f has m component functions. And each one of those component functions, and actually I'm going to use that term fairly often this semester, okay. each one of those takes in n inputs. So each value of u we're plugging in has n coordinates. Okay. So that's what f looks like. So now to take derivatives, we have to take the derivative of each one of these component functions, m of them, with respect to each one of the variables. Like if you have a function of 3 variables, like x, y, z, you need partial derivatives with respect to all 3. So I can have a partial of f1 with respect to u1, partial of f1 again with respect to u2, and I keep going. Partial of f1 with respect to un. So I've taken, and I just arrange these in the first row. Second row, same thing except it's partial of f2. I'm working on the second component function. And all partials with respect to u1, u2, up to un. So each row deals with a particular component function. First row is f1, second row is f2, and so on. All the way down to the last row, and I take the last component function, which is fm. So now I have all possible partial derivatives of all component functions of f arranged in this array, which you may recognize as a matrix. It is called a Jacobian matrix. So instead of having this f prime in single variable land, you have this. So this represents, you can think of it as actually also called the total derivative of f, because we have all the possible partial derivatives in here. So instead of f prime, we have this. Then we have the same thing for g. It's just that the number of variables are different. So instead of g prime, you have a Jacobian of matrix of g, which is a function of x. And we have p inputs, we have n outputs. So each row goes with an output. So partial of g1 with respect to x1, g1 with respect to x2, and so forth. Finally, a g1 with respect to xp, because we have p inputs. And then we keep going with g2, and so on, all the way down to the last row, where we deal with gn. Okay. Now, so now we have a derivatives of f and a derivatives of g all written down. So the multivariable chain rule is that the derivative, or Jacobian matrix, of f composed with g. So it's the same thing as f of g of x, that's true no matter how many variables you have, of x. It's evaluated at a particular x. Just as I multiply these derivatives here, which in that case is just plain old multiplication, I'm multiplying these too. Jacobian of f evaluated at g of x, so that gets plugged in there, times the Jacobian of g evaluated at x. And what we have here is matrix multiplication instead of ordinary multiplication. In the case of if there's only one, if there's only one output on this end and one input on this end, what you have is actually a dot product. So just however many variables you have, inputs, outputs of f and g, that determines what kind of multiplication operation you're performing. But this covers everything. So now, if I were to carry this out, I'm just going to take a quick poll here, see what any of you have seen or what you remember, because I'm going to redo it anyway. So how many of you in any class, whether it's 326 or maybe it's been seen in high school, I don't know, how many of you have ever dealt with multiplying matrices? Okay, now, again, honest answers. How many of you still remember how to do it? Okay, and that's okay, because I'm going to show you again anyway. Because also for benefit of people who haven't done it. Okay, I want everybody on the same page. So here's how it works using these two. So I'm going to do a simple case. So number of inputs and outputs in all cases is equal to 2. So the idea is G takes in inputs x and y, and gives 2 outputs that I'll call u1 and u2. But these are component functions, g1 of xy, g2 of xy. Okay. Now, similarly, f takes in, well, I'll use the same notation, u1 and u2. So just to reinforce, the output of g is the input of u. Same thing. Its f's outputs I'll call w, there's a z and w. And these have component functions also. So f1 of u1, u2, f2 of u1, u2. Okay. Actually, instead of u and u2, I'm going to use u and v. Sorry, I'll do my best to make my u and v's distinct. Just want to try to minimize the number of subscripts. Makes things messier. All right, so x and y are fed into g. U and v are produced as output. Those are fed into f. And then z, w is the output of that. Okay. So the Jacobian of f composed with g at any point xy is we're going to have partial of f1 with respect to u, partial of f1 with respect to v. So f1 occupies the top row. Partial of f2 with respect to u, partial of f2 with respect to v. So it's just what I'm doing over there, just more specific. And then I have, and all of this is evaluated at g. So that's what we have to plug into there. And then times the Jacobian matrix of g. Partial of g1 with respect to x. g1 with respect to y. g2 with respect to x. g2 with respect to y. Okay. And this is evaluated at x and y, just to clear what gets plugged into what, just like the single variable table. Now, to multiply these, I have two rows, 2 columns here. 2 rows, 2 columns here. Those dimensions have to match, or this doesn't make sense. And that's going to be true anyway, because the number of outputs of G has to match the number of inputs of F, or we're not even doing this problem. It doesn't make any sense. your result is going to be this many rows, this many columns. So I need to make space for 4 entries here. So how do you multiply them? What you do is you go across a row and down a column. You multiply corresponding entries, and then you add them all up. And the thing is, in the chain rule, you may remember from Calculus 1, there's a certain cancellation effect going on. And that helps you to keep track of, are you multiplying the correct things together? So here I have row 1 of F and column 1 of G. So partial of F1 with respect to U. Partial of G1 with respect to X. These get multiplied together. And then I move on to the next. So I go across the row, down the column. Keep that in mind. Across the row of the left, first one, down the column of the second one. Then partial of F1 with respect to V. Partial of G2 with respect to X. And the thing is, G1 we can think of as U. So I could write this if I wanted to. It's like U and this is V. So again, you see the cancellation effect of a chain rule. df1 du du dx, df1 dv dv dx. And all of this put together is a partial derivative of the first component of f of g with respect to x. Because the whole thing, f composed of g, is still a function of x and y. All right. So that's 1 out of 4 partial derivatives. To get this one, I'm going across the first row and down the second column. So this is row 1 of f again, column 2 of g. So I have partial of f1 with respect to u, partial of g1 with respect to y, plus partial of f1 with respect to v, partial of g2 with respect to y. But again, you think of g1 as being u and g2 as being v, because that's how I labeled them up here. And again, you can see the cancellation effect, df1 du, du dy, df1 dv, dv dy. So this whole thing is partial derivative of f composed with g, first component, but now it's with respect to y. So now we have all the partial derivatives of a first component of f composed of g. So I'm just going to rename these. So g1 is u, g2 is v. Now, that's the first row. For second row, we're going to work with the second row of f. So down here we're going to have row 2 of f, column 1 of g. And then over here we're going to have row 2 of f, column 2 of g. So again, I'm going to go across the row and down a column. So I multiply these together, and then multiply these together, and I add. So give it a shot. What am I going to have down here? So I'm going across the second row of f, but down the first column of g.
You're gonna have f2 over d over d.
Yeah.
Times the b, the first column over the g of b. Well, I mean,
Sorry, this is a u.
Oh, okay.
Sorry, yeah. I tried to make the v's really sharp, so you can tell the difference. All right, so what again?
What do you call that sign?
Partial.
Partial B over partial X.
No, that's a U.
I'm sorry.
Okay.
U, partial U over
Yeah.
partial X.
Again, my V's are going to be really sharp, so it's obvious. Okay.
Plus partial F of 2 over partial U. B.
Yeah, because we go across the row.
Sorry.
Okay. Everyone else help out too.
And then you're going to use partial V over partial X.
Yeah, and these have to match. Because that's how chain rule works. You have a sort of cancellation going on, even though I'm not supposed to call it that. Okay, and actually this is exactly the same as this, except here we're dealing with F1 and here we have F2.
F2.
So this is partial of second component of f of g with respect to x. And what's going to go in here is a partial of the second component with respect to y. All right, last spot.
Partial F of 2 over partial V. U. This,
Across, yeah.
I thought we were using this, the one to the right.
We are, but we're still going across this row.
I thought we were using that one, our fingers on that one, that'd be V. Isn't that a V?
That is a U.
I thought we were using the one next to it now.
No, we always use the whole row. Okay, here we're dealing with rows. We're going horizontal. Here we're dealing with columns, vertical.
Okay.
Okay, so that's why I have these arrows. Across this row, down the appropriate column.
Okay.
Okay, so
Times partial U and partial X. Plus partial F of 2 over partial V.
Yeah.
Times partial V over partial Y.
yes, okay. If anyone does not see this, now's the time to ask. So now it's so there should always be this situation of whatever you differentiate with respect to as an input of f corresponds to the same output of g. So remember, outputs of g and inputs of f are the same. So these should always match. Now here I gave them the same names to help with that, but that isn't always the case. But they may not be named the same, but they do correspond to one another. And just like in single variable calculus, you had like y equals f of x, and then you had and then some other variable, I'll call it s equals g of t. So then f of g of t, differentiate with respect to t, get df dx dg dt. Now in this case, these variables are not named the same, but the thing is, and if I want, since I'm calling this s, I could call this ds dt, and it would be obvious what I meant. And the thing is, even though these are not named the same, they still correspond to one another because the output of g that we're calling s now serves as the input to f that is now being called x. So here I've named them the same, so it's easier to see how we carry out the multiplication, but it all depends on what you're actually given in the problem. Okay.
Can we do an example of this?
Oh yes, I'm totally going to do it. I always do an example. But I want to show the general process. Okay.
Is this in the homework?
What?
Is this in the homework?
Well, yeah, there's lots of chain rule problems where you're carrying out this for some kind of scenario.
Well, I'm in the matrix.
That's just one perspective. You're not required to use a matrix approach. But I show it because there's two ways to look at chain rule in multivariable case. One approach, which most textbooks tend to use, is You have all these different situations for different number of variables, and they all seem different. But really, we're all the same thing. And it's this matrix perspective kind of unifies it, so that if you know how the multiplication works, that you're just multiplying derivatives, then you can handle any kind of problem that's thrown at you. Or you can treat it as a bunch of separate situations that you learn separately. So I don't really care which way you guys use for it. All right, so I'm gonna. Well, I have a few examples here. Let's see how many we have time to do. All right. Now, so F takes in 3 inputs, only has 1 output. G is a vector value function. Because F has 3 inputs, G has to have 3 outputs. Those have to match. And G has only 1 input. So I'll write down F is a function of 3 variables. Let's call them x, y, and z. So we use e to the z cosine 2x sine 3y. And then G is a function of t. It's a vector value function, has 3 components, which I'll call x of t, y of t, z of t. Just so you can easily see, the outputs of G correspond to the inputs of F. And those functions will be 2t, t, t cubed. Okay. So now what we can do is, if I were to write down f of g, this is just a function now, not the derivative.
Is the top cosine 2x or cosine z?
2.
Okay.
Remember, for z, I'm always going to put this little hash mark. Yeah. Okay. So the original function, if I put the 2 together, would look like e to the e to the z of t cosine 2x of t sine 3y of t. Then we can fill in what those are. E to the t cubed cosine 4t sine 3, oh, that should be t squared. 3t squared. Okay. Now, there's 2 ways to get the derivative. So f of g is a function of only t. So we could just take its derivative directly. But using chain rule, so that's going to be derivative of f evaluated at g of t times derivative of g evaluated at t. Now what do those look like in this case? F has only 1 output, it has 3 inputs. So we're going to have 1 row, 3 columns. So remember, number of rows always equals the number of outputs. Number of columns always equals the number of inputs. So that's why the derivative of f is going to have only 1 row, 3 columns. And what goes in there? We have the partial derivatives of f with respect to x, y, and z. Okay. That's f. G has only 1 input, t. Has 3 outputs, x of t, y of t, z of t. So it has 3 rows, 1 column. So that's what you're going to multiply together. Now, before we fill in what the specific derivatives are, remember, cross a row, down the column. And f of g together has one input, t, and one output, which is f of g of t. So what we're going to get here is only one entity. There's only one derivative to compute. So if we multiply together, go across the row and down the column, what are we going to get? Just like I did over there. So multiply corresponding entries and add them up. So you go across this row, down this column, multiply corresponding entries.
Partial of x times partial of, or is that dx?
That's dx.
Yeah, when it's a function of only one variable, I use a d.
Okay.
All right.
Times dx dt.
Yeah. Okay. Now, I sense some uncertainty. You want to take a shot at the second term?
Partial of f over partial of
Yes.
times dx dt.
Partial
Partial of
dc over dt.
Okay. Okay. Again, now's the time to ask if you're not sure where this is coming from. Please.
Is it okay to have partials and non-partials in the same? Right
Yeah,
now?
because what the partials versus d's.
Yeah.
Well, within each individual fraction, you should use the same symbol.
That's what I was thinking.
Yeah, yeah.
But they cancel the same way, or not cancel, but they work the same.
Yeah, yeah, yes. Yeah, the only reason I use a partial versus a d is this a function of one variable or several variables? It's just a notational convention. It's still a rate of change. Now, let's fill in what these partial derivatives are based on the original functions. So we have, okay. Oh, thank you for moving that. I need to be reminded, evidently.
Just get the guy inside, just turn it.
Okay. All right. Now, so these partial derivatives, just looking back at the original function, so that would be our respect to x, so it's going to be minus e to the z sine 2x times 2 sine 3y. And then partial with respect to y would be 3 e to the z cosine 2x cosine 3y times, and then with respect to z, it's going to be the same as the function. Okay. All right. So those are all derivatives of f with respect to its variables, and then g prime of t. We just differentiate each of these with respect to t. Okay. So now, when we, someone have a question?
Yeah, I'm looking at that.
Okay. Partial derivatives, which
Where
is
did
2.
that come from? Like the negative 2 e to the z.
Here's my function. I'm taking a derivative of each of this function with respect to first x, then y, then z. Okay. And I would have you guys do it, but I'm trying to fit more into time. All right, so all I'm doing is taking a derivative of the individual functions, f and g. All right, so this is fx, fy, fz. And this is no different than what you guys have been doing from the second section, so second assignment. Okay. And how are they combined? Well, that's what we have down here. So partial of f composed of g with respect to t. So we have fx, x prime of t. So same thing as over there, just writing it a little differently. Fy, y prime of t plus fz, z prime of t. So we have fx, but the thing is, don't forget it's chain rule, so you're plugging in your inner function. So z of t goes here. Sine 2x of t, sine 3y of t, times dx dt, which is, in this case, 2. That's this term. Then I move on to the next term. So df dy is here. 3e to the z of t cosine 2x of t cosine 3y of t times dy dt, which is 2t. All right, so this is x prime, y prime, z prime. Okay. Plus dz dt and I just plug in x of t, y of t, z of t throughout. And then we need dz dt, which is 3t squared. Now, the last thing to do is I wrote in placeholders, x of t, y of t, z of t, just so you can see where everything comes from. But now we need to fill in what those are. So wherever I see z of t, that's going to be t cubed. Right. What?
Talk about tedious.
Yeah, it is. And the thing is, that's the big difference between single variable calculus and Cal 4. Because doing more variables, all the examples that we'll see, like wait till you get to integrals later, it's doing some of the same manipulations, but it's all more tedious and there's a lot more to keep track of. And I know it's very easy to get discouraged, but now's not the time for that. No, I mean, you have to, there are two things that are essential for success in mathematics, and it's especially true in this class. One is patience, like more than ever before. And second, attention to detail. There's, as you can see on this board, there's a whole lot to keep track of. And that's why, like, if I'm teaching Cal 1, I can take 50 minutes and get through a zillion examples, no problem. And then in the same subject in Cal 4, I can hardly get through any, just because they take longer. And that's unfortunate. But yeah, it's not something that you can expect to just as quickly just because there's more to wade through. There's more notation to keep track of. And unfortunately, I have to do this faster than I would like to, but that's why I would strongly encourage you, regardless of how far we get today, look at my notes. There's examples in the notes. Other examples, whether I do them today or not, are there. Look through them. If you don't understand what you're doing, that's when you contact me. Okay? This is a 3 credit hour class, so that means you're expected to spend X amount of time outside of class, not just doing homework, but also digesting what's there to help you do the homework faster. And what I found, again, it's the 4th university I've taught at, USM students are far and away the worst at seeking help. It's definitely to you guys' detriment. So don't expect to just come in this class especially. You know, you sit here 50 minutes, it's like, okay, you come out, you walk out, oh, you get it. If you do, great. But if not, that's not the time to ring the alarm bell. That's time to use your resources, whether it's textbook or my notes or me, any of that. Okay. Sermon over. x of t is 2t. So I just fill in x of t, y of t, z of t throughout. And this could be simplified, well, only a little bit. I won't bother doing that. But finally, the derivative is complete, or will be as soon as I finish writing this. And is this a monstrosity? Then again, the other way to do it is if you went back here and took a derivative of this, as a plain old derivative with respect to t, what would you have to use? Product rule. And you would get these. You would get exactly this.
Where did your 2 come from on your first part of it?
This?
Yeah, where did that one come from?
Here. dx dt. Because it's 2t.
Okay.
Yeah, so we have these partial derivatives here, 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 but each one is multiplied by the corresponding derivative of these with respect to t.
That's what I was wondering.
Yeah, so 2 here, 2t, 3t squared.
Okay.
I have one last term, 4t sine 3t squared, 3t squared. And that's it. All
That's it.
right. Okay. Now,
So are we gonna have something like that on our tests?
that'd be like, I guess, a problem. Yeah, where you have, yeah. As you can see, there wouldn't be time for another. But yeah. Well, you can go to my site and see a practice test.
Oh, really?
Yeah, I need to add one more problem to it because, admittedly, the last one was a bit too short. Too many people got A's. But well, I like giving A's. I actually tend to give probably more A's than most. But I want to make sure that if someone gets an A, that it really is earned. But yeah, you can see an example of a changeable problem right there, and a solution. I give partial credit.
We gotta try.
Yeah, so don't leave anything blank. Give me something to give credit for. Okay, now, one thing in this section I actually covered earlier when I talked about implicit differentiation and how to do that more easily. That was actually using a chain rule. So, so you already have that in your notes.
It does slightly look like linear algebra.
What?
Linear algebra.
Yeah, well, the thing is, there's actually a saying that mathematics is the art of reducing all problems to linear algebra. And I happen to agree with that. Again, not necessary to get through this class, but it's one perspective. Well, you know, we have a number of math majors in here. You'll have to take modern algebra at some point. Modern algebra is very different from linear algebra, but there's a lot of, it works in a lot of ways. Now, I want to do an example of a different number of variables, just so you can see the contrast. Okay, here's a good one. So f, I don't want that one. Okay, I'll use this one. F is a vector valued function of x and y. So we have x squared y, x y squared. And then g is a function of single variable t again, like before. So it just has x of t, y of t. And that will be cosine t and sine t. All right. Now, because f has 2 inputs and 2 outputs, so all the partial derivatives, you're going to have partial of f1 with respect to x, partial of f1 with respect to y, partial of f2 with respect to x, partial of f2 with respect to y. Okay. Now these functions are relatively simple to work with So take the first function and differentiate it first with respect to x, which is what?
Partial.
Of this function. 2x, y. Y is a constant.
With respect to x.
Yes. Now, same function with respect to y.
X squared.
X squared. Okay. And now, that's the first row. Second row, this function with respect to x.
Y squared.
And with respect to y,
X. X. 2x. No.
2xy. Because y squared becomes 2y, 10 times the x. All right. That's derivative of f. Derivative of g. We just differentiate these components with respect to t. So, because we only have one input. So what will that be? Sine and cosine. All right, so then the derivative of f composed with g, which is now a function of t, it's the inputs of g, so that your combined function depends on the inputs of g only. Watch it right up here. All right, so then we multiply this times this, which I'll write this way, because g has two components. Components occupy rows. So, so I can write it like this. Now it makes sense for multiplying. So now you can go across the row and down the column. Okay. So again, multiply, add them all up. So what would that give you?
Negative 2x. Y sine t. Plus x squared cosine t.
Yeah. All right. That's the first one. We have because f of g is going to have two components. So we have cosine squared t sine t, and then we have cosine t sine squared t, because this is x squared y and this is xy squared. I'm just filling in cosine t and sine t for x and y, respectively. So if you differentiated this with respect to t, this part, this is what you would get, except I need to fill in cosine for x and sine for y. All right, last one.
Negative y squared sine t. And y
2xy
squared.
cosine t.
Yeah, 2xy cosine t. I mean, the only thing left to do is wherever I see x, fill in cosine. So minus 2 cosine t sine squared t plus cosine cube t, after I put everything together. And then here I have minus sine cube t plus 2 cosine squared t sine t. Okay. All right. So you figure out what are your derivatives that's based on, and how they're arranged depends on how many inputs and how many outputs each function has. Take all the partial derivatives, you carry out the multiplication, and then at the very end you can do any substitution. Like you can substitute your outputs of g into the inputs of f to have everything, because ultimately everything has to depend only on the inputs of g. So that here, in this case, our final answer depends on t. Okay. I'm going to see if I have to look at the upcoming schedule. I do want to spend more time on this. It's unfortunate that I was away. But I looked at the notes from Friday to see what Dr. Lee covered. Okay, so if I need to push homework back on this, I will. Again, I just need to look at all the dates and everything. But again, since we're out of time, now, look at my notes. I only got for 2 examples here. There are more examples of different combinations of notes. look at them. If you're not sure where the answers come from, email me, come see me in my office, I'm there all the time. So I want to make sure everybody's a chance to get on the same page. Because it is tedious stuff, but it doesn't mean you can't get it.
On your website, does it tell you, for this week?
Yeah, all the dates are there.